All right, now we're going to look at the relationship between temperature and pressure, which is called Gay Lussacs law. There's also a push to rename it, so you might see it called a Montan's law, depending on what textbook or website you're looking at. And what it states is if you increase the temperature of a gas, you will increase the motion of the particles. And this makes more collisions of the gas particles with each other and the walls of the container. And remember, as long as they're moving faster and they have more collisions means more pressure. And the temperature, remember, is based on the energy, the kinetic energy, or the speed of the particles. So as the temperature increases, the pressure is going to increase. Now, unlike Boyle's law, notice here both of the arrows are going in the same direction. So instead of being inversely proportional, now they are directly proportional. And so our law is not going to look the same mathematically. So we have pressure, instead of multiplied, it's going to be divided. So it looks like pressure over temperature will be equal to a constant. And when we have I didn't mean to do that, sorry. And we have two conditions. We have P1 over T1 equals P2 over T2. All right, so looking at our equation. Oh, one thing definitely want to make sure that you remember is that temperature has to be in Kelvin. This equation will not work if it's in Celsius. So even if they ask for the answer in Celsius, you have to put it in Kelvin. You'll have to put it in Kelvin, get your answer, and then subtract it back out if you want it in Celsius at the end. So how do we do that? Just to remind ourselves, Kelvin is equal to Celsius plus 273. All right, so just like before, we're going to set up a table. Atmospheres is a pressure. It says if the pressure is raised to 1.05 atmospheres, so that's another pressure. So we have a P, and then we have another pressure. Another pressure, and a temperature. It says what was the sample's initial temperature. So here's a P1, and they want the T1. So here's a P2, and here's a T2. So it was a little tricky with the wording. It says a sample of argon has a pressure of 0.92 atmospheres. That's the initial pressure, and they want the initial temperature. So I'm going to make a table. Again, they want the initial temperature, and the initial pressure is 0.92 atmospheres. They raise the pressure to 1.05 atmosphere, and the temperature is 30 degrees Celsius. Remember, we cannot have Celsius, so we have to add 273 to that, which gives me a temperature of 303 Kelvin. I find it's easier to do everything right in the table so I don't forget anything. So our equation is P1 over T1 equals P2 over T2. Plug and chug. P1 is 0.92 atmospheres. T1 is our question mark. P2 is 1.05 atmospheres. And T2 is 303 Kelvin. Remember, this is an equal sign, so we're going to cross multiply and divide. We're cross multiplying the two things that we know, which is the 0.92 times the 303, and then we'll divide by the 1.05 because that's on the side with the unknown, which is our T1. And when we get our answer is about 265 Kelvin. All right, next we have the initial temperature. So there's a T1. And it says the pressure is decreased from this, so that's a P1, to this, so that's a P2. And they want the final temperature, that's a T2. So we'll set up our table, P1, T1, P2, T2. P1 is 720 millimeters of mercury. T1 is 20 degrees Celsius. P2 is 360 millimeters of mercury. T2 is question mark. We can't have T1 as 20. We got to add 273, which gives us 293 K. Our equation is P1 over T1 equals P2 over T2. Plug and chug. I'll move it over here. P1 is 720 millimeters of mercury. T1, 293 K. P2, 360 millimeters of mercury. And T2 is our question mark. Again, we're going to cross multiply the things that we know and divide by the 720 because that's the side that we don't know when we cross multiply. Solve for T2, and our T2 is 147 Kelvin. Now, if they asked for this in Celsius, you would have to subtract 273 to get it in degrees Celsius, which would be about 100 and if we wanted it, we have 147 minus 273 be negative 126 degrees Celsius. Oops, I didn't want to do that. If we did it in Celsius, even though they didn't ask, but just in case you get a problem like that, if they ask for it in Celsius, to get it back to Celsius, we would subtract 273. All right, so just don't get stuck with this law by leaving it in Celsius. Always, always, always convert it to Kelvin. And there you go. Oh, let's double check. Make sure this is a direct relationship. I almost forgot to do that. So in the first one, example 1, our pressure went up. So our temperature should have went up. If T1 was 265 K, which we calculated, did it go up? Yes, it did. So we must have done it, at least we could have done it correctly. In our example 2, our pressure went down. And so our temperature should have gone down. It went to 147 K. It was 293. So again, according to this, we should have done it correctly. All right. Always double check to make sure that you didn't do it incorrectly. So if you would have goofed up your equation and done it the opposite, like put your P1 as your P2, and you could always find out that mistake because it would have went up when it should have went down. So those of you who struggle with the math, always use your common sense by double checking your inverse or direct relationships when you're done. All right, thanks for listening.